Hi, welcome back to this class, Transformer Decoder. This is a continuous class on uh, uh, one of the components on decoder. And here we talk about cross attention. Now, this part 4, let me take you through this part. Here is the decoder. Let me take the indicator. So here's the decoder. We've done part 1 with the output embedding, positional encoding. In part 2, we work with masked multi-head attention. And in part 3, we work with add, residual, and normalize process. And now we are working with the output from the add and normalize. It goes to multi-head attention. And also remember that we have the input, which is correctly represented contextually, and they feed in to multi-head attention so that we can create cross attention. So basically, key matrix with value matrix will be coming to here. So you can see these two arrows, and the Q from the out from this process, add, residual, and normalize, they will form altogether cross attention. So let's do the mechanism and do understand the mechanism and functionality of this work. Here, cross decoder cross attention means that we have encoder-decoder attention. So the inputs from the decoder, if we can remember, in the last part 3, we have decoder self-attention plus residual plus layer norm. We managed to get this matrix, which is the output, and represented by D. And we have also encoder outputs, which is represented by key and value matrices from our encoder. So both of them, they will, this is the encoder key and value matrix. So, of course, after linear projection. Then we would have, we will project to QKV. Now we need to apply linear projection, and we need to create weight matrices for query, for key, and for the value. And then we simply assume same linear projection, 4 by 2. So 4 by 2, and we assume they have the same weight matrix. Now, compute decoder query. So this is the decoder query. That's the decoder query. This matrix multiplied by WQ matrix. Okay. So here we would have this value multiplied by this column, this row multiplied by this column, and this row multiplied, the same row multiplied by this column. So for the two columns, here we have minus 1.25, which is this value, multiplied by 1 as it is, and here 1.42 multiplied by 0, then we will get nothing, and then minus 0.53 multiplied by 1, we will get as it is, and 0.37 multiplied by 0. So this is for column 1. Likewise, for the column 2, we will get these two values. So that's Q1, that's first row for Q1. Likewise, we will do for token, that's all for start token. This is for Anna token. word, the second token, the second word. So we will get this value for it, same operation, similar approach, and then we will get the same thing for AHEP, the token tree. So we have Q1, Q2, Q3, each one of them represent a token. Now, compute encoder keys and values. Of course, we would have the same matrix, assuming same matrix, we multiply it by this, the output from the encoder. So this represents keys and values, this matrix. We multiply each one of them by this weight matrix. So minus 1.39 multiplied by 1, then plus 1.3 multiplied by 0, it's 0, and then minus 0.35 multiplied by 1, and 0.47 multiplied by 0. So we will get for column 1 minus 1.77, and we get for column 2, same thing, this row multiplied by the second column. So we get two values, that is K1 and V1, because their weight matrices are similar, so we get the same value for them. And we said at the beginning, this is only for learning and for simplification. So for token-like, we will get with this two, because this encoder, they represent token-like, okay? This encoder, it's the first row is I, the second row is like, the third row is Rojava. And the query, the second row represent start token, and the second row represent ANA, Arabic translation for I, and the Q3 represent AHAB, the translation for English word like. So here we will have the values for K1, K2, K3, V1, V2, V3, and you can see three values. Now, after that, we will subject the value Q and K transfer under the scaling factor, which is 2, square root of 2, to softmax. Okay, so we will get this 2 first. We multiply Q multiplied by K transfer over scale, and then we take the softmax, and then we multiply it by V matrix, or V matrix, yes. So dk, assume we had d model is 4, dk is 2, and square root of 2.704. Now, for the token 1 start versus encoder tokens, so the Q comes from decoder, and K comes from encoder. So the start will work with I. So here we multiply the Q by K. The Q is this one. Do not forget, the Q is this one, and Q2 is this one, Q3 is this one. Now, we multiply them by K transfer, which is K1 is this one, K2 is this one, K3 is this one. So after doing all this calculation, we will get the value for each score, 1 to 1, 1 to 3, 1 to 2, 1 to 3, and then we do it for ANA token 2. Similar, we will get the same, we will get the similar operation, we'll get some values, and then for AHEP token 3, we will get these values. Now, if we take these values, okay, each one of these values, for example, 6.3189 divided by 0.707 to scale it, and 68069 divided by 0.707, and so on and so forth, all of them. So we will get the, for token 1, 501, and for token 2, 0.373, and for token 3. So each one of them is there. For token 1, that's the last value. For token 2, that's the last value. For token 1, that's the last value. For token 2, this is the last value. And after that, so these are the values that we have after scaling. So here we have this row 1, 4.47, and 4.81 and 5.01. And row 2, we have 0.338, 0.363, and 0.378. And row token 3, which is row 3, 4.9, 5.28, and 5.5. So softmax them. The first row represents the start token. So what we do, we will have exponential of this value and exponential of this value and exponential of this value, and then exponential of this value divide by the sum of this all exponentials. So 87.5 divided by 360.5. So we will get this value, and that's the softmax for it. So 0.243, 0.341, and 0.416. Now, remember that you should have the sum of this should be 1. 0.243 plus 0.341 plus 0.416. They should have 1. They should equal to 1. Likewise for Anna, we'll do the softmax for each one of them, and then the word Anna, the exponential of word Anna, divided by the sum of the all exponentials in the row. So we found the softmax for this one as well. This again, the sum of this plus this plus this should give you 1. Now, likewise, the same story for the token tree, and that's the value. And now you can see that the contextual here is, this is the highest. So Anna for token 2 then means that attends to ahab word. And for third one, for token 3, this is the highest, so ahab attends to itself mostly. And for this one, for start, for the start token, and we can see the highest is this one, 4.6. So start attends to ahab word token. Now, this is then we multiply by V weight V value V matrix and so that's the first row multiplied by this one. So this multiplied by this one. And then so 0.243 multiplied by minus 0.1.77 and 0.34 multiplied by minus 1.9 this row. So this multiplied by this row and this multiplied by this row, we should get the first row output, Likewise, for the second softmax, we will multiply it by, again, this one and this one, the two columns, we will get the value for it. And then again, we multiply likewise, we multiply ahab token 3 multiplied by value, which is this one. So we multiplied by this and this, you should get by the two columns, and you should get output 3. Now, this is cross-attention output, the results for it. Cross-attention means that we took K and V from encoder, and we took Q from decoder, and we get the cross-validation between them. Now we understand exactly what happens in the decoder cross-attention and why is that. So why we wanted to do that. So we are still translating I like Rojava into Arabic. أنا أحب Rojava. So here, the purpose of this process, decoder wants to generate the next word in Arabic, and therefore each decoder token already knows previously target token via decoder self-attention. But it also needs to look at the source sentence where it knows from self-attention, but it needs to know the source of each token that comes and to translate it. So it comes from the encoder, which is the value and K. That is the idea of it. So we said that query comes from the decoder after self-attention, residual, and layer, and then it represents what each target token wants to know from the source. And keys keys come from the encoder output, which represents where information is stored in the source sentence. So in source sentence, the information comes from the encoder, and the value also come from the encoder output, which represent the actual content to send it to decoder. So that's the mechanism for each decoder token computes similarity between its query and all encoder keys. This produces attention scores. And the softmax converts scores into weights, and each row should equal to 1, and each row will tell you the attention, how much attention, how much to focus on each source token. That's the idea. So that's the idea. So multiply weights with encoder values will give us a context vector for that target token. Now, that is the result, and this will, in the next part, we will try to get the residual, add this one to residual, add this one to the original output before I want to say before going into cross attention. So that's the idea. So here, once we get this this output, it goes to add a norm. We will get add a norm for it, and then will be added to earlier output from this process. So this will be added to the output of this one, and then normalize again. Thank you very much for listening. And if you have anything, just drop an email and find the links that we have. And that's how we work with this part.